Welcome. After learning about the analysis of distillation considering binary components earlier, we will be now be going to multi-component analysis for the design of the distillation columns. So in this lecture, we shall be learning about the approximate methods for the design of multi-component distillation column. The rigorous methods are taught separately in other subjects, so I shall not be going into the details of the rigorous methods. So in this particular lecture, we shall be learning about the key components which are the basis for the design of the multi-component systems. Then we shall be looking into the modified Fenske equation to find out the minimum number of stages, modified Underwood equation to find out the minimum reflux, and modified Gilliland equation for finding the actual number of stages. Why I am saying modified? Because all these equations have already been dealt with under the binary distillation column design. So first we come to the fact that why we need to have this multi-component consideration, because most of the fluid mixtures in the petroleum and the natural gas industries have more than two components. It is there, we know that there are so many components in the natural gas, right from the so many hydrocarbons, so many other impurities like nitrogen, helium, carbon dioxide, H2S, water, so on and so forth. So that is why it is not right to consider them to be a binary mixture, rather than we call them a multi-component mixture. And multi-component means whenever we have more than two components. So rigorous methods of analysis of this multi-component distillation would involve the solution of a coupled set of equations, and which are obtained by writing the mass balance, energy balance equations and the equilibrium relationships. And if you want to solve this kind of equations, they become quite time consuming. So first, for the first hand performance analysis, performance evaluation, what we do, instead of going for the rigorous calculations, we take some shortcut method which is based on some key component definitions, and using the or modifying the methods which we developed for the binary components. So first let us figure out what are the key components. So key components denote the components whose concentrations are specified in the distillate and the bottom products. Now this choice is arbitrary. It will be depending on the type of component recovery we intend to have. Accordingly, we shall be defining the key components. A column separates the key components to the desired extent. That means the basis of the design is on the separation of the key components. So in these key components, we have light key, which is abbreviated like LK, and these are the more volatile of the key components. So we have two components, whichever is more volatile is the light key, and the other one is heavy key, that is denoted by HK, and this is the heavier component. Now other than this light key and heavy key, we have the non-key components which are denoted by NK, and these non-key components distribute themselves between the LK and the HK. Then we have light non-keys. It means these light non-keys denoted by L and K are the components which are lighter than the light key, and the heavy non-keys denoted by H and K are those components which are heavier than the heavy key. What it means that the L and K will go along with the LK, whereas H and K will go along with the HK. We may have some components which are intermediate or distributed keys whose volatilities may be lying between the HK and the LK. In those cases, what will happen? These components will be distributing themselves between both the bottom product and the top product. So without going into the details of the derivation, what we do here is see that how the modifications have been done for the Fenske equation to find out the minimum number of ideal stages. So here we write the minimum number of equations. In this equation we write this equation. So we can find the A and B are the LK and the HK. So A is the Lk and B is the Hk. So this X means that the mole fraction of the light key component in the distillate, and this is the mole fraction of the heavy key component in the bottoms. In this case, we are not using B as bottoms, we are replacing the bottoms with W, so that we do not confuse with the component B. Okay, so we are using W as the bottoms. So this is the mole fraction of the heavy key in the bottoms. So this is the mole fraction of the heavy key in the distillate, this is the mole fraction of the light key in the bottoms, and this is the average relative volatility between A and B, between the top and the bottom of the column. Average, because as we know, the temperature and pressures vary along the distillation column. So we take an average between the top and bottom of the column. Now this can also be represented in terms of the fractional recoveries of the components. So this is how we are writing the fractional recovery. That means what fraction of the total amount of the light key or heavy key present have been recovered in the bottom product and the top product. So this fractional recovery have been defined like this, that this is the amount of the light key that is going along with the feed, and out of this how much has been taken out from the distillate. This is the amount of the heavy key component which has entered with the feed, and how much has been taken out from the bottoms, because even though they are light key, heavy key are supposed to go predominantly in the distillate and the bottoms respectively. However, some amount will also go in the other direction. That is why we need to define this kind of fractional recoveries, and this is generally never equal to 1 or 100%. We always lose some of the other in either the distillate or the bottoms. Now, if we consider the overall material balance of the column, considering there is only one feed, there is only one distillate, and there is only one bottoms. So we write this is the energy mass balance equation which we already seen, and if we just rearrange the equation and put the things in terms of the fractional recovery, then we find that the amount of the light key, the mole fraction of light key in the bottoms is given by the amount of the bottom flow rate, the feed flow rate, the amount of the mole fraction of the light key in the feed, and this is the fractional recovery. Now suppose we have any component J that is heavier than A. That means this may not be the key component. It may not be key component, but it is heavier than A. Then what we can do? We can use simply this same equation. The same equation we can use, but in this case we shall be replacing the B with J. So we can find that this is the way we can find out the minimum number of ideal stages if for separating a light key from a component which is not the key component. Now we go to the modified under root equation to find out the minimum reflux. Again, without going into the derivations of those equations, we write the final equation. So this is the equation 1 minus q, and this equation, and here we find that phi is this, alpha I is this. Now here we find the alpha I has been defined with respect to the heavy key, and the phi has been defined in terms of the heavy key, and this is the value of the V mean, this is the value of the L mean, and from this we can find out the reflux ratio from the mass balance equation. So this I am not going to detail. We shall be learning some more about these things when we go do some tutorial on this kind of problems later. Next we come to the Gilliland equation for the actual number of stages. Here we find that this is the curve for the finding the number of stages. Here we have defined two things, one is x underscore and y underbar. So this is the way we define. On the x axis we define r minus r mean by r plus 1. On the y axis we have n minus n mean by n plus 1. This r mean has been obtained from the under root equation, the n mean has been obtained from the Fenske equation, and from this if we get this value and this value, and the r value will be specified also generally which will be generally specified as some multiple of the R mean. So once I know the R value, once I know the R mean value, I can locate it on the x-axis and then go to this particular curve and read out the value of this y, which is n minus n mean by n plus 1, plug in the value of y, we know the value of n mean, and we can find out the actual number of stages. That means this is giving me the real number of stages required for a given separation. Now many analytical expressions have also been given. One of them is given here, that how to correlate this y with the x. So this is one of the, there are several other relations also proposed in the literature. So this is one of the equations which is used for finding the number of real stages from the reflux ratio. To find out the optimal feed location, this particular equation has been suggested by Kirkbride. So here we find that we have the value of Z, that is the compressibility factor, and these are the mole fractions of the light key in the bottom, the mole fraction of the heavy key in the distillate, and this is the bottom flow rate, this is the distillate flow rate. So by putting these values, and NR and NS are the number of trays, sorry, this is a spelling mistake, trays in the rectifying section, this is the number of trays in the stripping section, and from this we can find this particular ratio. So this will also give me where we shall be feeding the introducing the particular feed, and the Akasha modified this particular expression for the NR in terms of the total number of ideal stages, and this is the modification they have done to find out the number of ideal stages in the rectification section. And you can find more detail about this from these reference books. Thank you.